Ming, when you're ready. So
Yeah,
I've kicked off the session, so I'm starting to record it. Cool. So good morning, good afternoon, everyone, wherever you are. So basically, have you considered building a production-ready AI ML environment for a company? Have you thought about maximizing business value from your data, or considered running your AI ML workload in containers and use Kubernetes to orchestrate it? Have you thought about how you can maximize your hybrid cloud platform investment? Or how about DevOps approach for your AI ML workload? Or how about securing basically that AI ML workload? My name is Asher Benjamin, so I'm one of the new solution architects that's based in Auckland, New Zealand. New face, as you can imagine. So I've joined Red Hat in March of this year, so I'm part of Michael's team. So in today's meetup, you'll learn about Red Hat's community project, Open Data Hub. You'll learn how to use many of its tools to run your AI workload on Kubernetes platforms, such as OpenShift Container Platform. And using a perfect combination of slides and demos, we have Ming, who will share with us some insights on basically how OpenShift and DevOps can help you answer some of those questions that I mentioned earlier. So today we have with us Ming. So Ming is a senior solution architect at Red Hat. So he is the chief architect for public sector in Red Hat Singapore on cloud, container, and automation technologies. Prior to joining Red Hat, Ming has worked in engineering. He worked in R&D and technology leadership roles. So he has spent the last 20 years in open source, out of which 10 of those years was actively involved in high-performance computing and big data. Ming has also commanded multiple different technology leadership roles, from engineering, R&D, consulting, and, of course, architecture. So topics for today, as I mentioned, so running AI workload on Red Hat OpenShift Container Platform. So you'll learn about Red Hat community project Open Data Hub and how we can basically use many of those tools to run your AI workload on Kubernetes platform. We also have Michael Calizo. So in the last 10 minutes, we'll have a lightning talk that's done by Michael. So Michael is our senior solution architect. He's based in Wellington. Of course, he's a very, very familiar face in the New Zealand OpenShift meetups. So in this first series of lightning talk, Mike is going to share with us his opinion on why service mesh is so important. He'll also give us some ideas on what problems service mesh solves in this new era of application design and container adoption. As you know, so the session is recorded. So as Mike said earlier, we encourage you to ask questions, be interactive. We will also be running a couple of polls, so please be active and try and answer some of these questions. So from here on, I'll hand it over to Ming.
Cool,
and
great.
He can start his presentation. Cool.
Cool, no problem. I'm going to start to share my screen and go into presentation mode. Are you seeing my screen?
Yes, we are.
Yes, we can.
Cool, great. It's going to come up. Right. So, morning, everyone. So my name is what the folks on the call has mentioned. Right. My name is Ming. Right. So I'm a solution architect based out of Red Hat Singapore. Right. So today's topic, we're going to talk about a little bit more of AI ML kind of workload running on OpenShift together with the Open Data Hub project that Red Hat has. Right. So a little bit about myself, right? I think the guys have given a quick introduction about me, right? So I mean, for myself, right, I really started out in the high performance computing arena, right? So that was about 20 years ago, where I was developing code, provisioning huge amount of machines. So at that time, we were building code that was provisioning about 1,000 nodes of servers at a single point in time, using technologies like BitTorrent, to quickly, effectively, provision these machines, right? So that was, my HPC days dealing with, research projects, whether it's genome, whether it's, solving weather phenomenons, those kind of, those days sort of big data algorithms that you were running on supercomputers, right? So some of the supercomputers that, I was building was around this region, particularly in the Southeast Asia countries, where we were building high performance computing, right, and using operating systems like CentOS, Red Hat Linux, and even high performance interconnect like Mellanox or InfiniBand, right, to quickly disseminate those connectivities or messaging across the applications. And that's when I really move on to my next job, right, which is really big data, BI, machine learning, and a co-founder, right. This is interesting, part of my career where I actually founded a company with a colleague of mine, right. So we started a big data kind of machine learning company that dealt with tourism data, right. So we're building a tourism B2B, B2C kind of app. It's a mobile app, right, that allows people to come on to enjoy or to build their travel plans, right. So that was a travel itinerary company that I built, dealing with big data, machine learning algorithm, how to make the best recommendation to the customers, right. How do you mine data effectively across the web, right, to generate that kind of recommendation of that kind of preferences that customers really want to, right. So that was kind of my first step towards the world of machine learning, the world of big data, the world of business analytics or BI, right. And that's where I kind of found that what I really like about machine learning, and as I move around my career, right, which is next step is really the big iron SMP, right. So we're building big machines that are highly vertical, scalable, right. So in today's world, we talk about cloud computing, we talk about scale out technologies, right. But during that time, right, we were still talking about scaling up machines vertically by stacking hundreds of servers together. In those days, right, we were talking about hundreds of cores, terabytes of memory in like 100 servers together as a single SMP machines. So when you log into that box itself, right, and you do like when you log in and look at the number of CPUs that you have in the box, it's like hundreds of cores, right? Because all the machines are all connected together. And that's when the first time I dealt with Docker, right? Using containers like Docker to containerize the technology, right? To move them effectively, efficiently across the multiple servers, right? That's one of my first time using Docker and looking at how Docker is so much better than just installing a application on top of this big machine, right? Because you can actually locate it, right? You can actually distribute, with the kind of image capabilities that Docker has. And lastly, right, I joined Red Hat, right? And that is where, I really started out on the cloud, the automation and, containers and really about OpenShift, in the next, the last 4 to 5 years that I'm still with Red Hat, right? So let's really talk about the agenda that we're going to cover today, right? We'll talk a little bit about, what is AI ML, what are the challenges that, I see, with AI ML, especially on a Kubernetes or, in a traditional way of running it, why, what is ML ops, right, in particular, right? What's the difference between ML ops or DevOps? There's similarity, but there are also differences, right? And we'll move on to, really about, when you look at data science kind of workload and, looking back to my, past 20 years of experience and, when I look at the next generation of running data science workload, why containers, why, Kubernetes is effectively the next, platform that is really, really good for data science. And, and last but not least, is really about, the quick demo about, Red Hat Open Data Hub, right? It's a community project that Red Hat has, put together with, all the upstream projects into something that we call an Open Data Hub. And I'm going to talk a little bit about it and, and a bit of demo, right, of all the various elements in this Open Data Hub community project that we have today, right? So let's move on to a little bit. And what is, give a bit of background and context to what is AI ML, right? So, to different people, AI ML means a lot of different things, right? But there's 3 main categories, right? First, foremost, artificial intelligence, followed by machine learning, and followed by deep learning, right? So if you look at, my experience, right? When I look at big data, HPC, those sort of computational workload that is running, right? They are much very similar to, AI, ML, or even DR. But in terms of AI, right? It's a loosely term that encapsulates everything that we touch and do today. A lot of times when you say that you use your your Siri, you go whether you're logging onto Netflix, Amazon.com, with recommendation system giving you out the best movie of the year to watch, or or whether it's the the cat or dog pictures that it's being recognized or being classified for images, right? This all all sums up as a part of the artificial intelligence. But if you look at AI in general, right, and you look at the last all the movies that we have, whether it's C3PO or Terminator, right, those are actually all artificial intelligence. But when you look at a very narrow group of AI, which is what we are capable of doing it today, it's really about recognizing or trying to mimic what a human intelligence can do, right? So that is where we move on to a bit smaller scope, right, which is the machine learning, right? Machine learning in terms of recognizing or playing chess, right, for instance, right, or even recognizing a picture or a traffic stop sign, right? So that is machine learning, where the machine is trying to learn something, right, to pretend to be like a human, right? But as we all know, like machine learning, those algorithms, whether it's your Bayesian names learning algorithms, whether it's your classification or your k-means clustering, right, linear regression, and so forth, right? Those are limited in that sense, right? Because it's limited by the data input, right? That's where you have the next set of class of machine learning, which is deep learning, right? Deep learning is something that has been around for a while, but with the prevalence of GPUs today, right, it really makes deep learning much better, right? Because in the sense of how your computational power on a GPU card from, like, say, for NVIDIA, right, allows you to process the tensors much more effectively, right? So if you look at deep learning, it's essentially a class of problem that tries to mimic the human brain, right? For instance, right, because this is what the deep learning is all about. It's about neural networks, right? It's looking at how the brain has all the various neutrons, right, linking up all the neutrons together, right? And how do we process all these individual points? And from a deep learning world, right, it's really about scoring, right, go through all the various layers and outcome a final prediction, right, which is the probability score that you or I would like to have to say that, hey, perhaps this is a speech recognition software, right? Things like that, right? So this is all part of the next new generation of machine learning, which is deep learning, right? So then we move on to the challenges of AI ML. We talk about what is AI ML in general, but from the way I look at AI ML for the last 10, 20 years together with big data in high performance computing, I see kind of like the challenges that we face today, right? Especially things about data scientists coming together, right, and working on a set of problems, right? So you do have a in a data science world, right, you have a team of data scientists, you have a team of developers that work together, right? Because the data scientist is really focused on finding the right algorithm, right, doing the feature engineering and things like so forth, right, finding the right model, tuning the model. But the code, at the end of the day, the model needs to be deployed onto a platform that can be consumed by a wider enterprise core applications, right? So the model is really just giving you out the prediction, right? But in the state of things that it is, sharing is very difficult, right? Because when you look at how you effectively collaborate and share your workload, right, whether it's your Jupyter Hub notebooks and things like that, it's not easy, right? Because you can do it on your own laptop. That's what people usually start off with a Jupyter notebook running, playing around with the models on their laptops, and perhaps they commit it into a Git repository and start sharing it out. But the way we share out the notebook with the algorithms is not really consistent, and that's where I will talk a little bit later on why containers, Docker images really helps in that, right? And ultimately, when you start to deploy that workload, that model into production, it's going to be a challenge, right? Because a lot of times it's not just the data scientist that needs to be involved, right? It also needs to be the AI engineers and developers will probably need to take that model and build a REST framework around it, right, and deploy it into whether it's that SIT and into your production environment for the model to be consumed, right, by applications, right? Whether it's a RESTful API endpoint or whether it's the gRPC endpoint, right? All this, is what I, typically see in the current state of things, right? And we talk about, DevOps for ML, right? If you look at DevOps today for applications deployment, right? You have the CI, you have the CD, right? That, you build the application, you do your unit testing as part of the CI phase, and ultimately deliver it to maybe SIT or to our Active Factory repository before you promote or deploy it into production. But what happens in the ML world itself? It's similar, right? But there's going to be a bit of difference, right? I'm going to walk you through some of this and what I noticed when we talk about ML ops, right? You look at CI, but in a ML world itself, how do you run your experiments, right? Because from a data scientist perspective, I'm going to be very focused on doing feature engineering. I'm going to be very focused on finding or tuning the model, right? Giving a certain set of parameters, my model will get trained, I get a certain results. How do I find the best results? And how do I check that effectively when I'm doing, my tuning for days or for weeks, right? How do I keep track of all these results that's coming out from my training systems, right? And do I really want to check in my notebook in a Git repository? I'll talk a little bit about that later, and one of the problems that I see on the field, right? What about source control? When we talk about enterprise application development, we talk about source control of the source code, right? But what about ML? How do you keep track of your models effectively, right? As part of the training system, because you have the score, the results, you have the model, but how do you make sure that you're actually using the right model that will be deployed into production, right, with the right result that you want, right? What about training pipeline, right? How do you do a workflow, right, as part of your CI, right, that is needed typically for a ML ops perspective, right? What about when you talk about delivering into the environment? Are you going to deliver it as a VM? Are you going to deliver it as containers, right? Because today we're going to talk about containers. Why containers are give you that kind of beneficial benefits over VMs, right? What about model provenance and model tagging, right? How do you make sure that what is deployed onto your environment, you can actually trace it back all the way to the actual source code, right? To the training data that you have used to deploy the model onto your environment, right? And last but not least is really about reproducible model training, right? And about model serving. How do you serve that model effectively into your environment? Because the data scientist is really going to focus on building that model and perhaps just writing that model out onto a S3 bucket, right? You're going to serialize the model and write it on the S3 bucket. But how do you serve it in a very effective manner? And one of the things that we look at from a data science perspective is really reproducibility, right? When you have something deployed in the production, right, and something goes wrong, for whatever reasons, you want to be able to reproduce that, right? You want to be able to say that, hey, given this set of data set, even a set of models, right, I want to be able to reproduce what is happening, right? And that's where, when we talk about provenance, right, it really matters in a data science world, right? But what about, last but not least, is really about model monitoring and observability, right? If you look at, a typical enterprise application or any other application that's being deployed, you monitor them. Yes, you do, right? You monitor them for maybe for CPU, you monitor them for memory, you monitor them for network, or perhaps database transactions and things like that APM can provide you for. But in a data science world, you're going to be monitoring it very differently, right? You're going to monitor about the model performance, right? You're going to look at the scores that the model is happening in real time in production, right? Whether it's the F1 scores, right, or whether it's other ROC, those kind of scores that the model will return back to you, right, in real time. That is something that, from a data science perspective, you want to look at the performance. Right? When we talk about performance, we're not talking about the CPU memory. We're talking about how accurate the model is, right? So that is how do you monitor the models in real time so that you know that something is happening, a drift is happening, and you perhaps need to retrain your model in real time, right? And that's really about ML ops, right? So I took this picture. I really like this picture from Martin Fowler, right? He talks about CD for ML, and if you look at this whole cycle, right, from the model building all the way to productizing, right, all the way to monitoring, right? We talk about that in the previous slide, right? This is the cycle that a typical MLOps flow will actually go through, right? We talk about building your model, right, training your data, and going through an evaluation process, right? That could be as part of your pipeline workflow, as part of your CI, which is going to be a little bit different from a application development perspective, right? In a enterprise application, when you do CI, you're probably doing unit testing, right, of the application. But in a data science world, it's a little bit different. You're going to be doing testing on the data, making sure that the data, perhaps the schema, is accurate, and doing a quick evaluation of the model, doing part of the CI phase to say that the model is actually on par, right? So it's a little bit different from a traditional kind of application CI procedure, but the flow is roughly the same, right? And you start to productize the model with the chosen model, and you deploy it into your environment. In this case, we're going to talk about deploying onto containers, deploying onto OpenShift, right? Using part of the projects in Open Data Hub, and ultimately really monitoring the model, or even monitoring the data that's coming in to detect something called a model drift. The data drift that is coming in, because live data will always change over time, because perhaps the customer profile has changes, or whether the data source, there's some issues with the data source, or perhaps there's an issue with IoT devices because there's a skew in the data, and you need to be able to detect that in real time or in near real time, right? So that your model can perform up to par, right, with your requirements. Right. So one of the problems that I talk about is really about Jupyter Notebook in Git, right? So I understand that data scientists, they like to use Jupyter Notebook a lot, right? They perhaps checking into GitHub, GitLab, right? And because GitHub and GitLab gives you a very good visibility of, they can render the notebook perfectly, right? But when you look at source control, when you use, because of Git, when you look at source control and when you try to look at the delta and the differences of this notebook versus a previous version of the notebook, and this is what I'm going to get, right? In fact, if you look at the screen shot that I have, line 25, right, I only changed one variable of the NumPy array, right, from 2.0 to 2.0 to 4.0, and I reran the playbook and I checked the playbook in, right? And you'll notice that there are lots of changes, right? Because the way how a notebook, in fact, is a JSON file, and the fact that it's a rendered notebook that actually contains an image, because I was doing some visualization, because notebook, in fact, it is good, right? That's why data scientists loves it. You can, dabble with your code. You can, do your histogram, confusion matrix, all sort of visualization using Matplotlib on Jupyter Notebook. But once you check that in, it's going to be hard to see the differences, right? And that's why a lot of times when we start to productize the model, it's good, to have it in a non-Jupyter Notebook format where it's in, just like any other applications, right? You start to use, whether it's Python code, whether it's other, kind of languages, you start to check that into your Git repository so that, you can do, proper version control, right? Problem number 2, right? What about reproducible model training, right? Version control for data science, right? We talk about data lineage, we'll talk about source code, right? We also talk about model, right? Where do you keep these, data sets effectively in a model architecture, right? You will have your source code repository, which is Git, which is fine, right? You have your model.py, right, which is you check in Git, right? And Git gives you the that version control that you need. But what about data, right? What about the model, right? A data could be a CSV file. It could be a directory full of images. It could be from megabytes to gigabytes. Could be in terabytes, right? And your model outcome, right? Where do you keep that model, right? So a lot of times people talk about object store, right? Git LFS perhaps is a good option. Nowadays, people are thinking more towards a S3 kind of object store, right? You can, you need the version control because your data lineage, right, of different versions of the data, you need to be able to keep track of it, right? And you need to be able to keep track of the model that's been generated, right? So that you can actually link all of this together to to talk about when we need to reproduce, right, the training set, reproduce the model, right? You have the information, right, to reproduce it that accurately, right, as part of the training cycle, right? And we look at some of the tools out there, and some of them are actually in most of them are all in the open source world, right? First, you have the DVC, right? Second, you have the Pachyderm. Third, you have the ML flow, right? So DVC is actually a very cool project in the community that allows you to version control your data using a concept of Git, but the data is not kept at Git, right? Because Git itself has a limitation, right? If you want to keep it in Git LFS, by all means, but there are also other alternatives that DVC provides, like S3, which is a common backend that you will push your data towards it, and the data is version control using a metadata file, right, which is a .dvc here, right? This is how you version control inside your Git repository, but the actual data is actually kept in an S3 bucket. And you have other systems, right? These two are pretty common in the community today, which is Pachyderm. Pachyderm, it's one of the things that it focuses on pipeline, right? So you can do pipeline creations and data versioning. And MLflow is another cool project from Databricks, right? Databricks, one of the company behind Spark itself, right? So they created MLflow, right, to allow you to track your experiments, right? Your artifacts, right? Artifacts being that could be an image, right? Could be a text file, could be anything, right? And it will track your model training experiments, right? And I'll show that to you, as part of the demo later on in the session, right? Third problem, really about machine learning pipeline. And in the data science world, we talk about hyperparameter tuning, right? When you need to run multiple experiments across the environment, right? How do you evoke your training, or how to have a workflow in your training pipeline so that you can feed in different parameters, whether it's your different L1 ratio or alpha ratio, or any of the other parameters depending on the algorithm you have chosen, right? You need to be able to do this effectively, right, as part of your training pipeline, right? Perhaps it's pre-processed data cleanup steps that you need to do, right, followed by the training step, and perhaps by a post-analysis or quick validation of the model, right? So it really depends on how a workflow is being constructed, but in general, this is something that you would want to have as you get into a more serious form of data science, right? When you start to do more real work and for production, right? That's how I see it, and a lot of my other customers, when they look at how to take that training forward in the next step, right? And if you look at some of the tools out there, Kubeflow is interesting. Kubeflow has been around for the last few months to a year or so, right? Kubeflow is created by Google, right? So Kubeflow pipeline, or its hyperparameter tuning, underlying, it actually uses the technology from Argo. It's actually Argo Workflow, right? Because Argo itself has two projects. One is Argo CD and one is Argo Workflow. So Argo Workflow is more for a workflow perspective, and I actually have a demo of that later on. And MLflow is also there, right? But MLflow, the ML project itself is a multi-step, right? So it's just multi-step. It's not a DAG graph, right? And while Argo, it's both a DAG and a multi-step, right? Polyaxon, right, is another offering out there, right? It has its own optimization algorithms, where you can say that given a set of parameters, given a set of range, go do your job, right? And tell me what's the best results. And of course, the last and not least is Apache Airflow. All right, Apache Airflow is something very similar to Argo Workflow, but Airflow is more tuned towards data science, right? It's something that was created and open sourced by Airbnb. Okay. Next problem is really about monitoring drift, right? I talk about from the way how you build your models, how do you deploy your models, right? And how do you start to train your models in a multi-step or workflow manner, right? And last but not least is really about monitoring drift, right? One of the things that when the model is being deployed, just like any enterprise applications, when the model is deployed, right, you just don't stop there, right? You need to be always continuously monitoring the model for drift, right? Because drift, it's going to affect the model, because once a model has been trained, right, it has a set of parameters, a set of rules to generate your probability score, right? But because of data drift, because of various sorts of reasons, right, you're going to have a drift in there. And this is one of these two common tools, or rather open source tools, that we see that really helps for you to monitor the performance of the the model or even the data itself, right? You look at Prometheus and Grafana, right? Prometheus being the open source the open source monitoring tool, right? You can hook Prometheus onto your models, right? Because it's just going to scrape the Prometheus endpoint from your model, and I will talk about that a bit later on in the demo as how I use a project called Seldon to deploy the models onto the environment, right? So when you talk about scraping the models, right, you can scrape the models for matrices, right? Whether it's custom matrices or standard matrices like perhaps requests per second, or CPU and network and things and so forth, right? But of course, you can also start to monitor your data, right? Your data inputs, right? If your data is coming in through a data lake, right, you can start to look at that and plotting the matrix onto a graph like Grafana, right? So Grafana will give you, that view of a dashboard that that will be able to tell you, hey, perhaps my F1 score is not high, or my false positive, right, is too low, for instance, right? So things like that, you need to have that kind of monitoring kind of capabilities to be able to give you that view, and also perhaps integrating with alerts to say that, hey, something is indeed going wrong, please take a look into the system, right? And perhaps identifying that, hey, it's time to retrain your model, right? And then you start to do the continuous training, right? Looking at the data, looking at starting off from the data scientist perspective, looking at what is happening in the system, right? Perhaps it's a model drift, right, or it's a data drift, right? So you start to investigate on what is happening, right, and looking at the root cause of why the model is not performing up to par, right? But then again, what about A/B testing? When you deploy a model, it's not going to be static, right? Because in a typical enterprise application, you also will deploy A/B testing, right? Because the new application perhaps has a new color of the button, whether it's green versus blue, right? You need to be able to test it out, right? To see which consumer likes it better, right? It's the same for in the model world, right? Because when you do A/B testing, right? Because whether a model it's performing better in production may not be the same as doing testing, right? And you need to be able to deploy that, the two models side by side, right? Feeding in live data together with the monitoring into the system, right? To look at the scores that is coming out to say that, hey, this is indeed, for the next 2, 3, 1 month or so forth, right? This model is indeed performing much better. I'm getting better results from the model, right? My customers are getting happier. I'm getting less false positive, right? And that's one of the things that has not changed from enterprise applications, right? Because you need to do A/B testing, right? And how a container platform like OpenShift helps you to do that, I'll cover that in the next 2 steps. Right. So let's move on to why containers and why Kubernetes before we go straight into the quick demo. Right. If you look at containers, you look at Kubernetes. One of the things about containers, or rather images, it's really about the standardization of the training environment. In this case, it's the training code, right? If you look at how images give you that kind of immutability for your applications, giving you that the consistency that you need because of the various libraries, it's the same for a data science world, right? Because you need to choose a particular version of the Python, right? Whether it's 3.7.6, right, and a particular version of the runtime libraries, or whether it's Jupyter, right? Whether it's NumPy, whether it's your scikit-learn, whether it's your TensorFlow, right? All these are version specific, right? They all need to be be consistent, right? Because when I train my model, right, and another data scientist wants to use it, I can basically ship my images to him or her, right? Because then when he or she runs their image on her laptop or onto another training system, it's going to behave exactly the same way. It's the same thing as why we use containers for applications, right? It's that consistency that we want to achieve because everything is bundled in an immutable format in an image. Well, that also might include your CUDA libraries, right? Because if you're going to use GPU today, CUDA libraries, the version is going to be important, right? Any change in a minor version will possibly affect your results, right? And that's why when we talk about data science, we talk about why using images. It's really that immutable image that kind of benefits you get. The ship it, build it once, ship it around, ship it anywhere. right? And if you look at models deploying onto a container, onto a platform like Kubernetes, right? A model is essentially stateless, right? A model, whether it's in a Flask application, right, that exposes a RESTful endpoint, the model just that the app itself contains the model and effectively is stateless, right? So you can effectively scale that out efficiently, right, using Kubernetes, right? Because Kubernetes gives you that kind of control, right? If you need to have, right, whether it's scaling it out by the number of pods that you have, right, fronted by a service, right? So these are all Kubernetes concept, right? You can effectively scale this much easily in a Kubernetes world because they're all effectively stateless, right? Using perhaps things like the HPA, the horizontal pod autoscaler, you can scale your model up and down, right, as your demand rises and falls, right? And you can do something like a phase rollout approach, right? It's very similar to how enterprises applications are being deployed, right? You can do a rolling updates if you want to deploy a new model, right, into the system, right? Or even doing multiple trials, right? We talk about A/B testing or other type of data science specific testing like the multi-arm bandits kind of testing where you want to choose the best model for your recommendation system or for your modeling, right? So how do you do that in a Kubernetes world, right? That Kubernetes itself gives you that kind of capabilities and possibilities, right, to allow you to quickly deploy your model onto the platform, right? Allows you to scale effectively and even do multiple so-called A/B testing, right? Because you can say that hey, a certain number of traffic goes to model A, right? A certain number of traffic goes to model B, right? So really, it sums up to this four points, right? Really, when we talk about models deploying onto Kubernetes, right, it's really about agility, right? You can really spin up more of your pods, more of your containers, right, into their environment to scale as and when you need, right? Portability is effectively because we're building it onto images, right? Whether you're building the image on your laptop, right, deploying it onto a SIT or even to the cloud or to your fellow data scientists, right? The image is going to be consistent, right? It's the same thing as enterprise application, right? Flexibility, right? Because a lot of times in a container world, in a Kubernetes platform like OpenShift, right, you can easily do self-provisioning, right? Because I don't have to wait for my virtual machines. We talk about would you be deploying your workload onto virtual machines or containers, right? Preferably today is containers because from a Kubernetes platform itself, right, I can do self-servicing much easily, right? I can create a new project and I want to log in and launch my Jupyter notebook, right? I can start to play around with the environment without waiting, right, for my VMs to be provisioned, right? Lastly, scalability, right? Because talking about Kubernetes, talking about container platform, you can scale your workload as often as you want, right? You have that full elasticity that you need compared to virtual machines, right? So let's quickly move on to a bit of what is Open Data Hub, right? And before we jump right into demo, right? So Open Data Hub is something that Red Hat has created as part of a community project, right? So it is in fact a bunch of tools and technologies into this Open Data Hub that includes things like whether it's ingestion, whether it's streaming data, whether it's model serving, or rather things like workflows, right? It's all part of the Open Data Hub project that our goal for creating this really makes it much easier for the data scientists to consume, right? And actually it's powered by the Open Data Hub operator, right? So if you understand about OpenShift, right, you have the operator concept where you can easily install Open Data Hub with all the components into your environment and start to realize and utilize the tools that are available, right? And as part of the Open Data Hub project. And some of the tools that I mentioned earlier, right, and some of the things that I talk about, some of the challenges and some of the options that are available to solve those problems, those are actually all available as part of Open Data Hub, right? If you look at Kubeflow, Spark, TensorFlow, Prometheus, Kafka, Argo, Southern, Jupyter Notebooks, and there's actually a lot more of projects that's all part of the Open Data Hub, the Open Data Hub tool that we provide as part of OpenShift, right? So that's where you can start to easily install, right, and start to deploy and start, to build your first model quickly, right? That's really the gist of, why Red Hat created OpenHub, so that, data scientists can get started, quickly, easily on OpenShift itself, right? Before I jump straight into the demo, any questions from the audience, Mike?
So far, no questions. I think they are mesmerized with the topic that
Okay.
you shared. So let's go ahead and do the demo.
Let me go straight into the demo, right? So I have a OpenShift 4.5 running, right? So this is 4.5.7 running on AWS, right? So I'm going to go through a bit of, I think 2 or 3 demos about, using Open Data Hub. But first and foremost, let's look at the environment, right? So I have OpenShift 4.7, 4.5.7 running. I have let's look at the machine sets, right? I'm running it off in AWS. I'm running off in 1A, 1B, and 1C, right? So this is, OpenShift capabilities machine set that allows me to scale, effectively, easily on a cloud provider, right? But if you notice, I have actually created a new machine set, which is called with a GPU. Right? So what is this machine set? I have one machine, one node, right? And it's actually been provisioned already, right? And if you look at the details of the machine set, I am actually using, where is it? There we go. This is a P3.2x large. A P3.2x large is effectively if I'm not wrong, it's a single V100 instance with about 8 GB of memory. Right, where is it? Let's see this one. This should give me a better. Not here. There we go. Right, it's 8 vCPU and wait, this is 8 vCPU. It should be 8 vCPU. Yeah, 8 vCPU. Right, 8 vCPU with 61 gig of memory. Right, so and this is with one single V100 Tesla card. Right, so that's how, in an OpenShift environment, I created a new machine set, and I say that, hey, I need, how many machines, right? And effectively, I have, provision that environment, right, onto my node, right? And this is my node information. I have a P3 2x large, right? And so that's how, I provision a single GPU node, but I'm not ready to consume the GPU, right? Because OpenShift doesn't know that this is a GPU node, and that's how, I'm going to walk you through some of the quick steps. I'm going to install the operator, right? So I have a GPU operator resource, right? So if you look at, how OpenShift works today, is really, the ease of use because of the operator concept. And the operator that's needed for running GPU workloads there are 2 operators. One is the node feature discovery, and one is the other one, of course, is the NVIDIA GPU operator. Right? So the node feature discovery really says that, hey, please discover all the information about my node, right? Specific to your PCI devices, or whether it's which specific Intel chipset or network equipment that I have on this node, and it's going to label that accordingly, right? So if you look at the node itself, right? Let me go back to my machine set. Go back to my machine and look at my node. You can look at my YAML file. You look at all these labels, right? So this is done by the node feature discovery, right? And if I look at 10DE, right, I will see that the feature node PCI 10DE is present. It's true. So what is PCI 10DE? Right, PCI 10DE is in fact a PCI ID for NVIDIA. Right, so if you look at my screen right now, right, this is vendor ID 10DE. It's basically used for NVIDIA. Right, so the node feature discovery daemon set that's running will say that, hey, I have a 10DE PCI ID. I'm going to label my node onto OpenShift, right, onto Kubernetes itself, right, and that's where we look at the GPU operator. Where's my GPU operator? Right, so the GPU operator will take the 10DE, right, as a vendor ID, right, and say that, hey, this is indeed a NVIDIA, this node has an NVIDIA GPU. I'm going to install the drivers, right? So it's going to install my CUDA drivers, going to install my NVIDIA so-called plugin or device plugin. And that's where, you start to see that, hey, I do have a NVIDIA resource, right? So it's going to build the drivers, right? You're going to install the drivers, and you're going to install the device plugin for you, right? This is all part of the, the GPU operator framework that's created by NVIDIA. That really makes it much more easier for you to consume and GPU resources onto your environment. So let's take a look at the node itself, right? You will see that the node will have the resource allocated. Machines, go back to my node. Where's my GPU? Right, so I have allocatable of nvidia.com/GPU, right, of 1, right, because this node only has 1 GPU card, right. So now I'm going to start to consume the GPU card, right, using Jupyter Notebook. Right, I'm going to go to my Jupyter Notebook. I'm just going to log out. Right, go to my Jupyter Notebook that's been exposed via route that's installed by Open Data Hub operator. Right, I'm going to log into it. Okay, I have 1 notebook in there, which is my PyTorch Mist training example. Right, it's going to use GPU. This, right? So this is a very demo-ish example of using PyTorch, using GPU to do Mist. Mist being the image numbering set of data, right? I'm going to crunch through this using a concept of neural network, which is provided by PyTorch. I'm going to just quickly run through the code itself, and while it is running, I will walk you through some of this. Right, because I'm running as a notebook, right? I need, in this case, I need to install my Torch and Torch Vision libraries from Python, right? And if you look at some of the codes that I'm running, I'm doing a device count. I'm getting the device name. I'm checking whether CUDA is available, right? So part of this image that I'm using is actually pre-built as part of ODH, right? That has the CUDA libraries available, right? And you can really see that, hey, indeed, I do have a Tesla V100 card on this port, right? And this port, when I requested the port, I actually say that I need a GPU, right? So later I'm probably going to stop the server and show it to you, right? How do I request a GPU process, right? Because of the way, how Kubernetes work, right? I have allocatable, just like how you ask for a memory or ask for a CPU request, right? It's the same thing as I can ask for a number of GPU, resources, right? In this case, I'm just going to have 1. I'm going to say that, I have 1 GPU resource that I need. Kubernetes is going to deploy that port. In this case, it's a Jupyter Notebook port onto that node that gives me that 1 GPU, right? It's going to land on that node, and then I can start to consume the GPU resources on the node itself. Okay. So what it's going to do is it's running through the training, right? And I'm going to go back to my command prompt, and there's my watch. Say this will work. Just to show you an example, right? So I'm actually going into one of the NVIDIA driver port, right, and running a tool called NVIDIA SMI, right? So you'll see that, hey, I'm actually running a Python code, right? I'm consuming certain amount of GPU memory, right? And I think the workload has already finished, so it's 0% utilization, right? But this is in fact just showing you that, hey, this notebook is actually consuming a GPU resource from the underlying node itself, right? And how Kubernetes, together, with Jupyter Notebook, how we package ODH, right, gives you that kind of, functionality that, a data scientist can come on board to easily consume, right, GPU resources. Okay, right, that's for the first quick demo, right? Let's look at quickly on the pod itself, right, on the notebook. Where is my pod? Pods. Let's go to my ODH demo project. My OpenPLC. There we go. It's running. Right. So this is a notebook that's being spawned by the Jupyter Hub, and I will be able to see that it's actually being requested there. There we go. Right. It's requesting 4 CPU and 4 GB of memory with a single GPU card. Right. So that's how Kubernetes is aware that, hey, I need the GPU resources. I'm going to deploy this onto my node that I provisioned earlier on, which is the the P3.2 X large node itself, right? That's how it's been deployed and landed it, right? So that's a quick demo. I'm going to go back to my control panel. I'm going to stop my server, right? Just to show you a quick run through on how from a user perspective, how am I supposed to log in to get a notebook. So just start my server. Okay, right. So this is something that as part of ODH, we have packaged it, and you can choose your desired so-called notebook images. In my example today, in the demo today, I actually built one notebook with a GPU inside. It's part of the ODH packaging, right? So you have CUDA libraries inside it, and you can set your deployment size, whether it's your default small, medium, large, or other size that you can possibly customize, right? So in this case, I will choose large because of my training set, right? Otherwise, it's going to get killed by Kubernetes, right? And I define GPU as 1 so that saying that, hey, I want a single GPU resource, and off you go, right? It will start to spawn my notebook for me, right? So this is a spawn button. It shouldn't take a minute, right? So this is going to go ahead and spawn my notebook, right, with the parameters that I've requested into, and land that pod onto the GPU node itself, right? So it's going to start off by pulling off the image from the local repository, and it's going to go ahead and deploy that pod for me. Okay, let's move on to the next demo, right? So next demo is really talking about pipelining and Argo workflow, right? So in my project, right, I'm going to use something called Tecton, right? So I actually configure Tecton to do my CI, right? So let's look at my pipeline, right? So this is a pipeline that I've created that's basically built my training image, right? I have a using an S2I concept to build my training image and deploying it onto Argo workflow, right? To run perhaps multiple steps of training that I required, and it actually logs the result into MLflow, right? I'm going to serve the model op from S3 itself, right? So that's the pipeline that I have created, right? So let's quickly demonstrate that by triggering the pipeline. So I'm going to create this, and I'm going to let me prefer my Visual Studio, right? So I'm going to just make a quick change to my README, my README test, okay, like this. Testing demo push sync in. Then I push it up to my GitHub repository, right? The GitHub repository has been configured with a webhook, right, that actually triggers the Tecton pipeline. Right, so if you look at the pipeline runs, right, there we go. It's running, right? Duration a few seconds. Right, so the pipeline is going to run, right? Pipeline is going to run through the various stages. In a Tecton world, it's called task, right? And it's going to go through a couple of stages, and finally deploy the workflow, right? So let me just quickly run through the pipeline as the build is happening. Let's see, where's my pipeline? Oh, there we go. Right, so the pipeline is being built by different stages, right? For instance, like this is the one that let's see. Okay, this is the one that I'm actually building the image using Builder as part of S2I, right? So this is the S2I source to image task that as part of the pipeline, I'm actually building the image and actually pushing it out into the internal registry, right? That's all this part of the pipeline does. It takes the training code using S2I to build it and push it into the internal registry, followed by the Argo workflow, right? So Argo workflow, I'm applying the Argo workflow, where is it, right? I'm doing an OC create -f, right? Using the OCI image, sorry, OC OpenShift command line image, right? To applying the arguments to it, which is the OC create -f, creating the Argo workflow after I built the training image, right? So that's how the pipeline will work, right? Let's take a look at the Argo workflow. So Argo workflow is quite simple, right? It's a custom resource that has been deployed and created. The operator is actually running within the OpenShift platform, right? I'm going to do a deck, right, of multiple experiments running the image, right? I'm going to run the image with train.py, right, with a bunch of inputs parameters, right, as part of the Argo workflow, right? So I'm going to run through a bunch of flow with different parameters. In this case, I'm using ElasticNet from scikit-learn, right? Bunch of different alpha parameters and different L2 ratio parameters, right? So the workflow will run all of this as part of a graph, right? I'm going to show it to you in the next moment. Right, let's see. Oh, it's still building an image. Right, so if you look at Argo, right, so this is the Argo workflow screenshot, and in fact, I think I ran this like 2 hours ago, right? And if you look at the workflow itself, right, actually, this is a workflow, right? You can have multi-step or a deck implementation, and depending on how you will want the pipeline to be, it's really customizable, up to you to define the workflow that you are actually required to run, right? So this is the multiple steps that I have, and different parameters, alpha 0.2, ratio 0.1, 0.3, 0.3, and so forth, right? So this is how Argo workflow will work together as part of the CI. But I also did mention that, hey, I'm going to integrate my training code with MLflow, right? So look at the training code. The training code is a simple example, right? It's just using ElasticNet over the wine quality data set, right? So determining whether this red wine is good depending on a set of parameters, whether it's the pH value, when is it being harvested, and things and so forth, right? So this is a very standard data set that we use for demos, right? And if you look at the code that I've used, right? So this is MLflow, right? So MLflow gives you tracking capabilities for me to say that, hey, I want to log my parameters into the environment, right? And I can also log my model, right? So the one of the beauty things about MLflow is that I can track what the results that I have, or the parameters, and actually log the model so that I can actually correlate them if I need to be. Right? Let's take a look at MLflow quickly. Right, so this is MLflow. Let me take an example. Right, and you see that I have my matrix. I'm actually logging in my parameters 0.2 and 0.1. I have my output, which is my mean error score, my R2 square, right, my root mean square error, those kind of matrices that are being generated, right? And in fact, I actually can keep my models here, right? So this is actually provisioned using an S3 backend by OpenShift Container Storage that's part of OpenShift today, right? The backend is S3 and the model is being uploaded to a S3 bucket, right? And so in fact, you even do have the condo YAML file, right? So that is how the model is being tracked, right? Being deployed into S3, right, for version control, right? So now next step, I will actually be deploying the model that has been trained, right? You have trained the model, and I'm going to start to deploy it using the concept of Seldon, right? So I have the Seldon YAML file, right? So Seldon gives me the capabilities of deploying a model much easily onto a platform like Kubernetes, right? So in fact, if you look at this YAML file right now, right, it's actually very simple. I have the implementation of an MLflow server. I point it to my model URI, right? And then I say that, hey, I have a init container secret. So init container secret meaning that it just defines where my my credentials for my S3 bucket is, right? What is my AWS secret key, my access key, right, and so forth, right? So it's going to then deploy this into Kubernetes, right, and expose a route to it, right? So let's take a quick look at the pod that has been created for me. There's my pods. And then there we go. Right, so this is a classifier, sklen. And if you look at the logs itself, right? Just now I mentioned that I have the condo anaconda YAML file, right? It's going to take the YAML file. Where is it? Yeah, it's going to take the YAML file and start to install the dependencies, right? So that's how Seldon has made it so much easy for you to deploy your model onto Kubernetes itself, right? Just take that URI, right, with the model that has been uploaded, right? It's going to start to deploy the model and going to install the dependencies and to serve the model for you immediately, right? So you have the API v1.0 prediction endpoint, right? So I'm just going to do a quick demo of this. Right, this is my testwine.py. I'm going to send in the bunch of data, right, to the endpoints, and it's going to return me the prediction, right? So I'm just going to go ahead and run it. Right, it shouldn't take, yeah, that's fine. Right, so this is the prediction URL, right? So this is the route that's been exposed with the API / v1.0 predictions, right? I'm going to send in a payload, right? This is 11 variables, right? Which is, pH, of the grapes, and so forth, right? It's going to come back with a prediction, right? Whether it's good or bad, right? I think the prediction score ranges from, 3 to about 10, right? 10 being the perfect score, right? And this is how, 5.8, a moderate range, a moderate quality of wine, right? This is how, I'm going to, post my data, right, into the model, and out comes the response back from the model, right? All part of Southern, being the package, the packager, right, as part of ODH, right? ODH gives you that kind of of capabilities to easily deploy your model, right? So that's really the quick demo that I have, right? Any questions from the field or from the audience?
Yeah, we have actually questions here, Liming. First question is actually coming from Byron, and I answered this, but he said, is it required to have GPUs for machine learning?
No, it's not. It's definitely not required. So from my experience and from I talking to other customers, right? GPU, well, GPU is good to have, right? But not all sets of problems requires GPU. Right, really depending on the problems, data sets, and what you're trying to do.
Yes.
Right. A lot of times, GPU will give you that the boost that you would like to have, but sometimes it's not necessary. Right. It's really about experimentation.
Correct. Yeah. So another question from Ben: why the NVIDIA GPU operator? That I think. Why did you use it and not the special resource operator?
Okay. Right. Because I think what I did was looking at how our collaboration, of course, with NVIDIA, right? And the NVIDIA gives me, I think it's a bit similar, but not the same. As in, NVIDIA is going to support that GPU operator, right?
Yeah.
And together with the node feature discovery, right? And that's how I use it in tandem together, right? To allow a user to really consume the GPU resources. And I think today, when we look at OpenShift, I think they will be more moving towards the NVIDIA GPU operator, as it's being supported by NVIDIA itself.
Yeah, cool. That's good. Another question from Nigel is that any examples of monitoring with Grafana or Prometheus?
Monitoring
data concept.
Yeah. So what happens is that in typically Grafana, let's see whether I have an example here. Okay, maybe I'll go through another. Oh, actually, yes, I can use this. Right, I'm going to do this. Right. Yeah. So this is something that you will be using to say that, hey, I want to expose my matrix through Prometheus, right? Prometheus being run today as an operator on OpenShift, right? So whether you're deploying your own Prometheus, right, or you're using OpenShift to monitor your user workload, right? You will define something called a service monitor, right? A service monitor basically.
His question is there any alternative for this on Open Data Hub, or is it just Grafana or Prometheus showing data?
You can. Yeah. So today is really just Prometheus and Grafana, but of course, depending on how you expose your matrix, you can be using APM tools, or you could have your own way of monitoring. There's lots of possibilities, right? But Prometheus and Grafana gives you, right now, because Prometheus, Grafana is all part of CNCF, right? And the framework is there. It makes it so much easier for you to scrape and present the data.
Yeah. Another question is from Hill. We use Databricks heavily. What would be the advantage of OpenShift versus Databricks? Both are agnostic. So I can for this as well, but yeah, you can give your opinion.
Yeah, I mean, perhaps I think the gentleman is mentioning about Databricks online, right? Databricks on the cloud.
Yeah.
Yeah. So I mean, Databricks itself, right? Databricks. It gives you the environment, right? It's just like any other cloud providers
Yeah.
today. I see them Databricks, whether it's AWS SageMaker or Azure learning, Azure machine learning, right? They all are running on the cloud. They gives you the kind of platform that allows you to consume, right? But a lot of times when you look at how you want run your workload on premises, right? And that's how at the back end they all are probably running Kubernetes and containers, definitely, right? But if you look at some workload that is going to be run on premise, right? OpenShift is a good platform because when you start to deploy that workload onto your cloud, you could be doing your data science work on premise because your data is a lot, right? It's on premise, you have terabytes of data on your localized data lake. But once the model is being built and you want to start to deploy, and your consumers are maybe perhaps from the public, right? You can deploy the container in the same way as you deploy it on premise to the cloud, right? Using the same environment, which is OpenShift. Right, so that is where I see how OpenShift plays a part, right? About the consistency of the operation wise, and from a application developer perspective, how will you deploy that into the environment?
One more question from Gail. Python is one of the language that you can use in ML in our organization. We have people using C++ and R to build model. Does OS or any open source available in Open Data Hub has support on any of these languages?
R is interesting. I've not used R for quite some time, right? R itself, well, yes, it's something that I seen data scientists uses it, but I don't think it's as common as Python. But from the open source community, I don't see that in OTH. But from the open source community, you can definitely still use your R models to build your R models. That's fine. Right? Same for C++. Right, C++, if you need the specific algorithm that is only available in C++, right, you can still build it, right? And then there's no restrictions there at all.
Yeah, we're a bit over time here. I'm supposed to do my my service mesh lightning talk, but we'll reserve that next time, eh? But it was a great session. It was good. I think people just left because it's already 1:12 right now. But it was really good. And thanks for your time, Liming.
Yep, no worries.
Cool.
Thanks, Liming. Thanks, guys.
Yeah, we'll stop the recording and the broadcast as well. Thanks, guys.